Hello, welcome to How Vec Works in Rust 3! This is the main function that we've been exploring. Episode 1 was creating a Vec and pushing 5 elements. Episode 2 was creating a Vec with a capacity of 5 and the Vec macro. Episode 3 is indexing. Remember this macro? It will create a Vec with 1, 2, 3, 4, 5, and 6. Here's the definition. It changed! In the last video, the box new associated method was used here. Now, we use the box new intrinsic. Apparently, this is a dramatic improvement in stack usage for large Vecs. Let's recursively expand this macro to see what it'll do. We remember this from the last video, but this is different. We use the box new intrinsic to box up our array of 1, 2, 3, 4, 5, and 6. The box new intrinsic is how the compiler creates new boxed items to be allocated on the heap. It's used in the box new associated method too. We saw this in the last video, but it's a bit different now, so I wanted to include it here. So we box up our array and turn it into a Vec using the wildcard slice into Vec associated method. This turns the boxed slice of 1, 2, 3, 4, 5, and 6 into a Vec of 1, 2, 3, 4, 5, and 6. Now this Vec is called V. These two indexing operations should be familiar to most of you. The first one gets a reference to the first element of V, and the second one gets a reference to the second through fourth elements of V. How does Rust let us use the same operator for both of these? And how does it know that these square brackets are indexing operators? We're about to find out. We'll start with this method, index. I'm sure you can guess what it does. To begin to understand this method, we must learn about its trait, index. The index trait controls the indexing operation for Rust. It has one generic type, IDX. Note that IDX doesn't need to be sized. The trait has an associated type output that also doesn't need to be sized. It also has an associated method index that takes in a reference to self and an IDX index. The method returns a reference to the output type from above. How does this trait control the behavior of the square bracket operators? Like most things in these videos that initially seem not to have an answer, the compiler does it. This trait is treated specially by the compiler. It is a lang item, which means that it defines some kind of special behavior. Let's make an example. We'll start by making this struct index test. It holds 3 usize values. Imagine now that in our main function, we define an index test called index test with 67, 69, and 1738. As someone who tutored computer science, I met students who would assume that you can do this to get the value they're looking for. This is how you would actually do that, by the way. If you were to try this, the compiler gives you 3 warnings telling you that you cannot index into a value of type index test. Makes sense. At the bottom, it says to try rustc-explain E0608. Here's what that tells you. At the top, it tells us what we did wrong. We attempted to use index on a type which doesn't implement the standard ops index trait. It gives a similar example to ours, trying to index a U8. It then tells us a solution. To be able to index into a type, it needs to implement the standard ops index trait. It gives us an example. We can index into a Vec. So now we know how to fix our code. We have to implement standard ops index on index test. By the way, there are many data structures that benefit from indexing. This is not one of them. This is only for demonstrative purposes. With that in mind, notice how we get the respective values stored in index test when we index by using a match. Now we can successfully index into our index test type. If we were to print our 3 results, we would see 67, 69, and 1738 printed to the console. Why do the square brackets call the index method? Well, the compiler replaces the call like this. Since index is a lang item, the compiler knows that this is how it needs to treat the square bracket operator. The compiler has special knowledge of this lang item and so knows to replace the desired calls. I will, of course, link some reading about lang items in the description. This attribute defines the error message that we receive when we try to index a type that doesn't implement index. We just saw this error message when we tried to index into index test before we implemented the index trait. When index isn't implemented, the compiler will let you know exactly what went wrong. These attributes add an alias to an item so they can be searched for in the documentation generated by RustDoc. So in this case, you can write square brackets instead of writing index, and you will still find the index trait. I'll also link a short explanation of this. This attribute is part of an experimental const trait system being designed right now. This attribute will not be there in the future. It indicates that the trait can function in a const context. It's part of what will likely be a years-long project to get const traits fully functioning with ergonomic syntax. I'll link some info about this project as well. The output type is the type that will be output by our indexing operation. If we indexed into a vec of strings, we'd expect to get a string. Output indicates that type. The index method is the method that actually controls the indexing behavior. It takes in the IDX index and returns the output. So it takes the type capable of performing the index and returns the corresponding output. That's the index trait. This trait controls the behavior of the square bracket operators, aka the indexing behavior of collections we all know and love. This is the implementation of the index trait for vec. Guess what? This is the only index implementation for vec. Notice that this structure mirrors the index trait, obviously, because we're implementing index. Output is I output, and the index method takes in an I index and returns a reference to output. What is I? There are three generics involved in implementing index for vec: T, I, and A. T can be any type, A must implement allocator, and I has to implement this SliceIndex trait over a slice of T. Basically, vec can only be indexed by types that implement this trait. The SliceIndex trait is quite large. It has a generic T that doesn't need to be sized, and it inherits from the private SliceIndex sealed trait. We'll see what that means soon. First, this is the compiler's error message when we try to use this trait on a type that doesn't implement it. We've all seen basically this exact error message before. This is what happens when you try to index a vec with an integer that's not a usize. A vec can only be indexed using usize numbers. Rust guarantees this so that you never index negatively into a vec, preventing a whole class of bugs at compile time. SliceIndex has 7 associated items. It has an associated type output, the output type returned by its methods. It also has 6 associated methods. These methods should be familiar to people who have worked with other growable array structures in other languages. Get tries to index the vec, returning an option containing either the successfully retrieved output or none. Get unchecked does the exact same thing but without any bounds checks, returning a pointer to the output. Notice that this method is unsafe. It doesn't do any bounds checking, so it could lead to undefined behavior if used improperly. I'll link the undefined behavior link in the description. Index does the same thing, but instead of undefined behavior or returning none, it panics when the index is invalid. This is the method we'll spend the most time analyzing. Each of these methods has a mutable version that gets a mutable reference to the indexed element instead of a shared reference. This lets us mutate the part of the collection that we indexed. The output type and these 6 methods are part of the SliceIndex trait. From here on, we will almost exclusively be looking at the index method because it's the most relevant to the index trait, unsurprisingly. So now we mostly understand the SliceIndex trait. It gives indexing functionality to certain types for the purpose of indexing into a collection. We still don't know which types this is implemented for. The private SliceIndex sealed trait bound will help us figure that out. Remember that this is a trait bound. That means that any type that implements SliceIndex must also implement this sealed trait. So the sealed trait is an empty trait that lives in this private module, private SliceIndex. The authors don't want any types other than the ones they chose to implement SliceIndex. Thus, they require inheriting from the sealed trait inside of this private module, and inside of this module, they implement sealed on all of their desired types. This way, no other types will be able to implement SliceIndex without the express desire of the authors. These are the types that can implement SliceIndex. We won't be looking at these 3 types because they are replacements for other types. These types will eventually be replacing their respective ops range types, but for now, they just use the implementations of the old ones, so I won't include them. I'd encourage you to check out the incoming API rework because it's pretty cool. The new types will implement copy and into iterator instead of iterator like the old types. I'll link the RFC explaining the motivation behind this change in the description. These are the types that we will be looking at in this video. We will look at how each one implements the index trait, one by one. Sealed binds the SliceIndex trait, which binds the I generic parameter of the index implementation for vec. The index trait implementation of vec controls the indexing behavior we requested in vec. Namely, we want the first element of v and the second through fourth elements of v. However, there are many more ways to index a vec. Like I said, we're going to look at all of them one by one. We will see how to index a vec using a usize, a range, a RangeTo, a RangeFrom, a RangeFull, a RangeInclusive, and finally a RangeToInclusive. Notice that these are the same types that implement the private sealed trait. Well, except these two, but we'll explain them towards the end. So we'll be finding out how each of these types indexes V in its own unique way. We'll start with usize. We index V with 0 to get its first value. You should be familiar with how to index a vec by now, but I will do an extremely quick explanation of indexing anyway for completeness purposes. This is what our vec V looks like in memory. These are our indices. We start with 0, and each index is a new element based on its number in counting order. So when we let first equal V of 0, we set first as the first element of V, which is 1. So we are indexing our vec V with the number 0. Let's see how the index trait controls this behavior when we index with a usize. Here's vec's implementation of index. Remember, this is the only index implementation for vec, so no matter what type we index our vec with, this is the method that will be called. We will be seeing this method many times because it's called every single time we index our vec. We have two main things to look at here, our associated type output and our index method. Our associated type output is IOutput. Remember that our indexing type must implement SliceIndex. Also remember that the SliceIndex trait has an associated type output. This is that type. As for the index method, we index with our type I and return our mentioned output. Since we indexed with the usize type, the I generic of the index trait is usize. The index method takes a reference to self and an I index. It returns a reference to output. Internally, this method calls the IndexIndex method. This parameter looks confusing, but we can figure it out together. These two stars mean that we are dereferencing self twice. Self is a reference to vec t. So when we dereference it twice, we dereference the reference to vec into a vec, and then dereference the vec into a slice. After twice dereferencing our reference to vec into a slice, we reference the slice so we can pass it into the index method. Here's what that process looks like with the types expressed. How does vec dereference into a slice? It uses the deref trait. This trait is a laying item describing the behavior of the star operator. It has an associated type target and an associated method deref. I'll link the documentation of deref in the description. This is vec's implementation of the deref trait. So when you use the star operator on a vec, this method is called. Inside, it calls the asSlice method. This method takes our vec and returns a slice of its memory buffer. It calls the sliceFromRawParts function. We won't look at this function, but it basically just calls the aggregate raw pointer intrinsic that we will be seeing later. It takes a pointer to the beginning of our vec and our vec's length and glues them together to create a slice. So the asSlice method is called in the deref method in vec's deref trait implementation. I'll link a Stack Overflow thread explaining this line. So we pass our vec dereferenced into a slice into the IndexIndex method along with our I index. That brings us to the index method for slice's implementation of the index trait. Slices are a contiguous sequence of elements in memory. Since vec can be dereferenced into a slice, vec's index implementation simply refers to slice's implementation. Notice that the indexing generic I must also implement the SliceIndex trait. This tilde-const syntax allows us to use trait methods in const contexts. This is experimental and technically does not have this same syntax anymore. I'll link some resources in the description. For now, we can just treat it as any other trait bound. I must implement the SliceIndex trait. This implementation looks remarkably similar to vec's implementation. The associated type is identical, and the index method looks very similar as well. Inside, we simply call our IIndex's index method, passing in our slice. The index method is defined here, inside of the SliceIndex trait that we saw earlier. Remember that we're currently looking at how we get the first element of V using a usize 0 to index. The SliceIndex implementation for usize looks like this. The output type is T. Makes sense. We're indexing one element, so we expect to get T in return. The index method looks like this. We take in a usize and a slice of T slice. We return a reference to T. Internally, we use intrinsic indexing to get our desired element. So the compiler will replace this code with a call to a platform-specific indexing operation. At this point, we've extracted our desired index from our vec's underlying slice and returned a reference to it. We got this reference from the SliceIndex index trait method called by the index method in Slice's implementation of the index trait. This method was called in the index method in Vec's implementation of the index trait. This method was called when we indexed into V with a usize 0. Now, first will be a reference to the first element of V. Printing this value to the console, we see exactly what we expected, a message saying usize 1. That all seemed very complicated, but trust, all of the complexity that we just saw functions to make the code more general. The more we analyze this API, the more you'll understand the motivation behind its design. So we just saw how we can index into a vec using a usize to extract a single value. Next, let's see how to index a vec using a range to extract a range of values. To demonstrate, we'll index into V using this range, 1.4. This is an exclusive range, meaning that it goes from the first value to the second value, but excludes the second value. So this range will be 1, 2, and 3. The type is called a range. This is what the range type looks like. It simply consists of a start and an end. Both of these are of the generic type IDX. In our cases, this type will always be usize because we're using the range type to index into a vec. Notice that the range type is not copy. There is good reason for this. I'll link 27186, which explains why. Remember how we won't be checking out these three indexing types? These are being added specifically to fix this issue. These new types implement copy and into iterator instead of just iterator. I will also link the RFC explaining these new range types so you can get a better understanding of why this API change is being made. So we expect this indexing operation to get us the second through the fourth elements of V using this range 1.4. We expect to index the sequence 2, 3, 4. Let's see how this version of indexing works. Like we said, this is the only implementation of the index trait for vec, so we will be passing through this method every single time. We index into the dereference slice and get to the only implementation of the index trait for slice. We will also be passing through this method every single time. We call the index method of our SliceIndex type I, passing in our slice. Here is the implementation of SliceIndex for the ops range usize type. Our output type is a slice of t. Think about it. We're expecting to get multiple values when we index, so returning a slice of those indexed values makes the most sense. The index method takes in our range, our slice of t slice dereferenced from our vec, and returns a new slice. First, we do a checked subtraction of self.start from self.end. There's no guarantee in range that start is less than end, so we have to ensure that on our own. If start was greater than end, our range would be malformed for indexing, and it would be nonsensical to index our vec with that range. So if our checked sub succeeds, we extract our variable new len, which will be the resulting length of our new slice. If the checked sub failed, meaning that self.start was larger than self.end, we call this SliceIndexOrder fail function. The SliceIndexOrder fail function takes a usize index and a usize end. It returns the never type, meaning that it will never resolve to a value. This function is a dead end. This is a panicking function. This is the const panic macro. It enables panicking in a const context. We're going to briefly skim through its contents. It's a pretty large macro. It has two matchers and transcribers. The second one simply calls itself. It allows the user to leave out some information. The first one is the more important one. It defines a function doPanic and calls that function. Inside of that function is another macro called const eval select. We've seen this macro before in other videos. It is even bigger than the last macro. There are three matchers and transcribers. Only one of them isn't just a call to the same macro. The second one. We're rushing through this, so feel free to pause. Basically, what this does is create two functions, one for runtime and one for compile time. It passes these two functions into the const eval select intrinsic function that we've seen before. Here's a reminder of what that looks like. It chooses which function to run, either runtime or const, and runs it. So that's the const panic macro. We pass in these four arguments. From context, we can now infer that the first message is intended for const panicking and the second for runtime panicking. The third and fourth arguments are to format the second message. Let's recursively expand the macro. So the doPanic function is defined and called with our index and end parameters. Inside of this doPanic function, two functions are defined, runtime and compile time. Both call a panicking function called panic format that we won't be looking at. I'll link its documentation in the description. The panic messages are different depending on if we're in runtime or compile time. The const eval select function decides which of these two functions to run. So this is just a fancy panic that lets us panic in a const context for performance gains. If you want to know more about it, I'd encourage you to look at the documentation, which will of course be linked in the description. Remember that this panic is called when our range is malformed and start is larger than end. See the error messages? SliceIndex start is larger than end, and SliceIndex starts at index but ends at end. Okay, so we panicked using the SliceIndexOrderFail function if our checked sub failed, meaning that start was larger than end. Next, we check if self.end is greater than slice.len. So if the end of the range is larger than the length of the slice, we call this SliceEndIndexLenFail function, passing in self.end and slice.len. This function looks remarkably similar to the last panicking function that we looked at. The main difference here though is the panicking messages. These messages read, SliceEndIndex is out of range for slice, and RangeEndIndex index out of range for slice of length len. So this panic happens when the end of the requested range goes beyond the end of the vec. Instead of accessing memory beyond the vec, we will obviously panic instead. Note the use of the const panic macro again. So we panic using the SliceEndIndexLenFail function if our range end is larger than our slice length. Lastly, we call this getOffsetLenNoUBCheck function. We pass in slice, self.start, and new len. We dereference and then re-reference the result. The function is unsafe, but it's okay because we just verified the validity of our range with our last two checks. This is the getOffsetLenNoUBCheck function. It takes a const pointer to a slice of t pointer, a usize offset, and a usize len. It returns a const pointer to a slice of t. Remember that we dereference and then re-reference the result of this function. Dereferencing the pointer gets us the memory of the slice, and then referencing it gets us a reference to that slice, which makes it usable. The first thing that we do is thin out our pointer. We don't need the length metadata of the slice pointer anymore because we're making a new slice with a new length, so all we want is the memory location, which is what we do here with this cast. Next, we offset our pointer by offset using the intrinsic offset function. This moves our pointer forward by offset memory slots. For our offset, we gave the function self.start, so this call to offset will move our pointer to the beginning of our requested range. Lastly, we call this aggregate raw pointer intrinsic with pointer and len. This intrinsic takes two arguments, ddata and mmeta. It returns p. We've looked at this function in a previous video, but it's actually different now. However, it still does the exact same thing it did before. The function itself takes the ddata and the mmeta and glues them together into a pointer. In our case, data is our memory location pointer and meta is our length. This intrinsic takes those two and combines them into a wide pointer containing both the memory location and the length. This means that we get out a new pointer, a pointer to a slice with its length as metadata. The trait bounds here enforce this pattern with types at compile time. So we aggregate our pointer and len into a slice pointer and return it to the caller. This function is a little confusing, so I've made a visualization to help us understand it. We'll start with the in-memory representation of our vec v. We call the getOffsetLenNoUBCheck function to get the second through fourth elements of v. Remember that we did this with our range from 1 to 4. We pass in a dereferenced slice to v, 1, and 4 minus 1. 1 is the beginning of the range, and 4 minus 1 is the length of the range. The first thing that we do is thin out our slice pointer. This gets rid of its metadata that contains the length of the slice. Now it simply points to one location in memory, the beginning of v. Next, we offset the pointer to the beginning of the range. This moves our pointer to the second memory slot because we offset it by 1. Last, we aggregate our pointer and the length of our range. This gives us a new slice pointer to our desired range of elements. That's how the getOffsetLenNoUBCheck function takes a slice pointer to our memory and gets a new slice pointer to our requested range. So our new slice pointer is dereferenced, then re-referenced as the return value for our index method on Range's implementation of the SliceIndex trait. This method was called by the same two index methods that control all indexing behavior for slice and vec. So we index into V with the range 1.4 and get a new slice of our requested values. Printing our result to the console, we get range 2, 3, 4, just like we were hoping. Notice that this slice lives inside of V, so we are directly referencing V's memory with a new slice, not creating a separate clone. This is because this is an indexing operation, so if we wanted to modify this area of V, we could do it. However, we'd be using the index mute trait, not the index trait. Next, we'll see how to index a vec using this range, .2. This is called a RangeTo. It goes from the beginning of the collection to 2. The RangeTo struct is similar to the range struct, just without the start parameter. In the case of RangeTo, we only need one parameter, end. Notice that RangeTo implements copy. That's why this type isn't being replaced by the new range types. So this type of range, where the start bound is the beginning and the end bound is defined by us, is called a RangeTo. We should be expecting to index this sequence, 1, 2. Let's see how we use the RangeTo struct to index into a vec. We go through the index method for vec and for slice using our RangeTo type. The SliceIndex index method for the RangeTo type is pretty simple. We construct a new range from 0 to self.end and call the index method of the new range. This index method is the index method for the range type that we just went over. Remember that it checks some conditions and then gets a new slice without any bounds checks using the getOffsetLen noUBCheck function. Since the RangeTo type is meant to go from the beginning of the collection to self.end, we can just put 0 in place of self.start and reuse the index method we just saw. This is an excellent example of code reuse. We don't have to repeat any of the logic from the range type. We just make a new range from 0 to self.end and it operates exactly how we want it to. So that's the index method of RangeTo. We went through both the slice and the vec index methods to get the result of indexing with our RangeTo. Printing the result to the console, we get RangeTo 1, 2. This is the slice representing the range from the beginning to the second element. This is extremely useful for scenarios where we only want to see the first n elements of a collection. We can just index using a RangeTo. Next, we'll look at the RangeFrom type. This range is a RangeFrom. It goes from 3 to the end of the collection. Notice that RangeFrom is basically the opposite of RangeTo. RangeFrom contains one field, start. It doesn't have an end field. This type is also not copy, just like range. This is one of the types that is being replaced by the new range API. So we expect this range, 3 ... to give us the sequence 4, 5, 6. Let's see how we index a vec using a RangeFrom. We shouldn't be surprised to see the index implementations for vec and slice making a reappearance. This is the SliceIndex index method implementation for RangeFrom. Like all other SliceIndex index methods, it takes our RangeFrom and our slice and returns a new slice referencing the indexed memory. First, we check if self.start is greater than our slice's length. If it is greater, we call this SliceStartIndexLenFail function, passing in self.start and slice.len. This function is another panicking function that calls the const panic macro. The two panic messages are SliceStartIndex is out of range for slice, and RangeStartIndex out of range for slice of length len. So we can infer that this panic happens when the start index of our range goes beyond our slice's length. Like the other panicking functions we've seen, this prevents us from accessing memory that lies beyond our slice. So we call the SliceStartIndexLenFail panicking function if self.start is greater than slice.len. Next, we call this unsafe getUnchecked method, passing in our slice. This is the one time that we'll look at another one of the implemented methods on the SliceIndex trait. In this case, we have called the getUnchecked method for RangeFrom. It takes our RangeFrom and a const pointer to our slice. It returns a const pointer to the new slice we get by indexing. The method itself makes a new range from self.start to slice.len and calls the new range's getUnchecked method. Notice that this new range goes from our start value to the end of the slice, just like we wanted. This is the getUnchecked method from SliceIndex implemented for range. It has the same method signature as the getUnchecked method for RangeFrom, unsurprisingly. First, we call this assertUnsafe precondition macro. We've seen this macro before, and we also know that it doesn't run in release mode. It checks, in debug mode, that end is both greater than start and less than len. We are going to ignore it for brevity's sake. Safety is guaranteed here by the calling conditions. Slice is not dangling and our range is in bounds of our slice. First, we get new len by subtracting self.start from self.end. This gets us the length of the slice that we want to return. Next, we call the getOffsetLen noUBCheck function that we saw earlier. We pass in slice, self.start, and new len. Remember that this is the definition of the getOffsetLen noUBCheck function. It thins our slice pointer, offsets it by self.start, and aggregates it into a new slice pointer using new len. This gets us a pointer to our new index slice without any bounds checks. So we get a pointer to the new slice and return it to the caller. We called the getUnchecked method on a range from self.start to slice.len in the range_from getUnchecked method. We called the getUnchecked method in the index method. Notice that we dereference the pointer, getting a slice, and then re-reference the slice so it's usable. Our new indexed slice is returned by the index method. Passing back through our slice and vec index methods, we arrive back at main where we indexed v using a range_from 3 to the end of the vec. Printing our result to the console, we get range_from 4, 5, 6, just like we were expecting. We got the values of our vec from 3 onward, 4, 5, and 6. How great is it that we can easily extract the last n elements from our vec, and everything we've covered up to this point is all handled by one generic method from a trait. Wow! Moving on to my personal favorite range type, RangeFull. The 2 dots represent the RangeFull type. RangeFull is simply a unit struct. It has no data. These 2 dots represent indexing the whole vec, so we expect to get this sequence from our indexing, 1, 2, 3, 4, 5, 6. We expect to get in return the entire vec. Let's see how the RangeFull type does this. Of course, we first have to pass through our trusty vec and SliceIndex implementations. Well, how wonderful is that? The index method literally just returns the input slice. In fact, all 6 SliceIndex trait methods do the exact same thing. They just return the input slice. Very cool stuff. We just saw these a few seconds ago, but we must remind ourselves of their importance. So we're just returning v's underlying slice. Printing to the console, we see RangeFull 1, 2, 3, 4, 5, 6, exactly like we knew it would. So we get a slice of v's whole memory using the RangeFull index. We are now moving into the territory of a completely new type of range, the inclusive range. This range here is called a RangeInclusive. Most inclusive ranges can be represented as regular ranges. All you have to do is add 1 to the end parameter. However, there are use cases for this syntax. I will link the RFC which explains the motivation for including this syntax in the language. The RangeInclusive struct looks similar to the range struct with some important differences. The start and end fields are private, just in case the authors want to change the representation in the future. Time will tell if this ends up being necessary. The more important difference is this field, a bool exhausted. This field indicates whether or not the RangeInclusive has been exhausted while iterating. You might have heard it said that you shouldn't use an inclusive range when you could use an exclusive range, and this is why. Iterating through a RangeInclusive requires more state than iterating through a range. However, in practice, this is very minuscule, and the compiler might optimize it to look the same as an exclusive range. Though, there is an argument to be made for pinching every cycle to save on compute cost. It's up to your discretion, I guess. RangeInclusive is also our third and final non-copy range that's being replaced in the new Range API. So this is a RangeInclusive. We expect it to return this sequence from the second to the fifth element of V, 2, 3, 4, 5. Let's see how to index a vec with this new type of range. We still call our 2 most trusted index implementations for vec and slice. This is the SliceIndex index method implemented for RangeInclusive. First, we check if the end of our inclusive range is equal to usize max. If they are equal, we call this SliceEndIndexOverflowFail function. This is a panicking function. It simply panics with the message attempted to index slice up to maximum usize. Notice that this function doesn't use the const panic macro, opting instead to simply use panic. Well, I'm not sure why this is the case, but it might have something to do with the error message not having any formatting requirements. Let me know if you know in the comments. The SliceEndIndexOverflowFail function only runs if self.end is equal to usize max. Next, our range inclusive is turned into a slice range using the IntoSliceRange method. This method takes a range inclusive and turns it into a range. It explains how it does this in its body. If the range inclusive is not exhausted, aka if it's not at the end of its iteration, then we want to slice start to end +1. If the range inclusive is exhausted, we slice with an empty range. After we get our new range from our range inclusive, we call index on the range. Remember that this is range's index method from the SliceIndex trait. It checks two conditions and then gets a new slice using the getOffsetLen noUB check function. We use this method to index into the range we made from our range inclusive using the IntoSliceRange method. That's how range inclusive implements the SliceIndex index method. This was called by our two most trustworthy slice and vec index implementations. So we indexed v with the inclusive range 1 ... equals 4. Printing our result to the console, we get range inclusive 2, 3, 4, 5, like we expected. This represents the second to the fifth elements of v, where the final element was included in our range inclusive. Last, but certainly not least, is RangeTo inclusive. This range type is exactly the same as RangeTo, but inclusive on the high end, so this RangeTo inclusive will index from the beginning of v to the third element. Here's the RangeTo inclusive struct. It has one field, end. It doesn't need start because it always starts from the beginning of the collection. We expect this RangeTo inclusive ... equals 2 to give us this sequence of v, 1, 2, 3. Let's see how RangeTo inclusive indexes a vec. For the final time, we call both the index method for vec and the index method for slice. Here we see the SliceIndex implementation for RangeTo inclusive. We simply create a new range inclusive from 0 to self.end and call index on that new range. Remember that the index method for range inclusive checks that the end doesn't overflow and then indexes into an exclusive range made from our inclusive range. So we make a new range inclusive starting at 0 going to the end field of our RangeTo inclusive. This is another great example of code reuse. We barely have to write any logic because all of the logic has been handled for us in the more general case of range inclusive. That's how RangeTo inclusive implements SliceIndex. We called both the slice and vec index implementations to get here from using our RangeTo inclusive to index v. Printing our result to the console, we get RangeTo inclusive 1, 2, 3, like we expected. Here's all of the indexing types that we've gone over today. We indexed with a usize to get a single element, and a range, a RangeTo, a RangeFrom, a RangeFull, a RangeInclusive, and a RangeToInclusive to get a slice of elements. We explored the implementation of the SliceIndex trait for each of these that controls their indexing behavior. Remember that these are the types that we wanted to look at that implement the sealed trait required for the SliceIndex trait. Notice that we haven't covered these two. I chose to save these two types for last because they operate pretty differently from the others. We'll see why. First, let's look at the SliceIndex index method implemented for a tuple of the OpsBound type. So this is the index method for a tuple of OpsBound. What is OpsBound? Bound is an enum with three variants: included, excluded, and unbounded. It represents one end of a range. Think back to all of the ranges we've seen up to this point. They all consist of two pieces, a beginning and an end. The beginning and the end are all either inclusive, exclusive, or unbounded. This enum just represents those two pieces as one enum. Using two of these, we can index with any bounding behavior we want without the ... syntax. First, we convert the two bounds into a slice range using this IntoSliceRange function. The function takes a usize len and a tuple of bounds start end. It returns a range. We begin by matching the start bound. If it's included, we just extract its value. If it's excluded, we try to add 1, panicking if we overflow. If it's unbounded, we use 0. Next, we match the end bound. If it's included, we attempt to add 1, panicking if we overflow. If it's excluded, we extract its value. If it's unbounded, we use len. Lastly, we just return a range from start to end. So we took our two bounds and turned them into a range. We create this new range and call the index method on it. We've seen range's index method a few times. Here's a final reminder of what it looks like. So we index with our new range created from our two bounds and return the output slice to the caller. That was index for a tuple of 2 bounds. Next, let's see what's going on with this index range type. In a way, we've already seen index range. Index range is identical to range except for 2 crucial differences. The start field is guaranteed to be less than or equal to the end field, and these 2 fields are usize, not generic. This means that the range will always be well formed for indexing, and some micro-optimizations can be made. I'm pretty sure that the compiler will often replace range with index range when indexing if it can verify that start will always be less than or equal to end. So how does indexing with an index range differ from indexing with a range? It's basically the same, just with one condition check omitted. All we have to check for is if the end of our range is past the end of the slice. If it is past, then we panic using the SliceIndex fail function. If it's not past the end, meaning that the range is fully encased within the slice, we call the getOffsetLen noUB check function that we've seen before, passing in slice, self.start, and self.len. We remember this function. It thins the pointer, offsets it to the beginning of our range, and aggregates a new slice pointer with our pointer and the length of our range. So we get our desired slice from our index range if self.end is less than or equal to slice.len, panicking otherwise, and return the result to the caller. So that's the index range type. It exists solely to make optimizations by guaranteeing that start is less than or equal to end. Now we've been over every single one of these types, indexing into our Vec V with each one in main. That was episode 3 of how Vec works in Rust. I hope you've learned something about Rust's index API. I also hope that this has taught you some lessons about the power of abstraction and smart type design. All of this functionality is funneled through 2 methods, and all of the behavior implemented on one trait. The relationships between data types here is astonishingly well done. Go forth and do good with this knowledge. In the next and final How Vec Works in Rust video, we will explore how Vec is printed to the console using Rust's formatting API. Thank you so much for watching. I had a lot of fun making this video.